But we can't say the things that we normally say on our podcast.
That is correct.
So I couldn't say something like beep.
And
Like
I definitely couldn't say beep, 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 and beep.
I am not doing this bit.
Too late.
He's too deep in. Anyway, this is Alex Austin from Ronan Geek Official Podcast. And in the room with me today, I have...
Plebeian Pirate Adam.
And
just Rob.
And just Rob. And we are here to advertise Ronan Geek Official Podcast. We are a geek news and comedy podcast direct out of Windsor, Ontario, Canada. So if you want some Canadian flavor on your geek comedy news, make sure to give us a listen each week for gaming, movies, and TV. We'll give you some reviews. We'll give you some spoilers. And we'll give you probably a lot of other stuff you didn't ask for. So there you go. So join us wherever you find your podcast. And we look forward to having you listen to us.
Yay.
Hello, listeners of the Mad Scientist Podcast. I'm your host, Chris Cogswell, here today joined by Dr. Yvette Cendes. So Dr. Cendes is a postdoctoral fellow in astronomy at the Harvard-Smithsonian Center for Astrophysics and studies what she likes to call giant space explosions. Dr. Cendes, I'm so excited to have you on the show today.
Thanks for having me.
Yeah, of course. So giant space explosions, can you dig into that a little bit more for our listeners? What is it that you actually study? What is it that you research?
Sure thing. So when I say giant space explosions, I mean literally the biggest explosions that we know of in the universe. So these are supernovae. So when a star basically is at the end of its life, a very massive star, and blows itself apart in a giant space explosion. There's other space explosions as well. So one is called a tidal disruption event, when a black hole, basically a star, wanders too close and gets ripped apart. Then that will, release a huge amount of energy as well. I do also search for things that are colliding with other things. So tried to look for LIGO gravitational wave mergers, signals from that and stuff like that. So there's a lot of different giant space explosions out there. What I'm mainly interested in is the radio radiation that these explosions give off.
Okay, so you're actually looking at this kind of signals of those explosions, the way that we can tell that they're happening. So I guess as a first question for the listeners who are, not as well versed in this stuff as you are, of course, and frankly, I am not as well versed in this stuff, even compared to some of the listeners, I'm sure. What is it particularly that you're looking for in those radio signals? Like, what do you hope to learn from them?
Oh, yeah. So that's a great question, of course. It's so what we're interested in, basically, there's the electromagnetic spectrum, as you probably learned at some point or didn't learn in high school. It stretches on one end, the longest wavelength. So like the wavelength will be meters long, is radio wavelengths. So centimeters to meters in terms of like the height of the wave. Once you get down, you're going down infrared, you get to optical, those are nanometer waves, and then you can go even smaller and smaller all the way down to X-ray and gamma ray. I'm down at the radio end, so like as I said, the biggest waves. What you're getting there is basically, or the main radiation I'm studying, there's of course different kinds of radio radiation you can study from outer space, but this is if you have a shock wave going outward, you're going to have basically that shock wave slamming into anything in that surrounding medium or area. And that is going to give off radio radiation. Basically, if you have electrons spiral in magnetic fields that are created by the shock wave, that's called synchrotron emission. And that's what we're seeing in the radio. And that's what I study.
Interesting. Okay. So what kind of underlying questions are you, I guess, trying to hope to solve with that data? Like, are you looking for how these explosions occur? Is it sort of why they occur or when, or is it more nuanced than that?
So there's a few things. So often what I'm doing, I'm not like usually not discovering new things that we haven't seen. Usually you'll see like a supernova in optical light. So you have automatic sky surveys that will basically look all over the sky now every night at all sorts of galaxies looking for new supernova. So supernova, when they go off in visible light, one star can outshine an entire galaxy. The trick is also, on average, a galaxy of our size will only have one supernova, maybe a century, maybe two. So as a result, you want to look at a lot of galaxies. And so they'll see this in optical. And then we'll go and radio and try to find it, basically, and see if we see any radio emission. That'll tell you that, oh, there's a lot of stuff around the stars, the shock waves going out that's interacting with it. And that can tell you a lot about if the star ejected that material, for example, before it died, maybe what caused the supernova explosion in the first place. That's like something you're looking for. The other reason it's really important to look at radio is you can study radio emission many years after the initial explosion happened. So you can have the optical light fade, you can have, all the other kinds of radiation fade, but because the shock wave is still going outward, if there's still enough material, you'll actually still see radio emission, maybe even decades after the initial explosion, many, many years after there's no other radiation that you can detect from it. So that's also very powerful in terms of telling you what exactly is happening, how is the system evolving over after the initial shock. So
it's so fascinating that when I got interested in science as a kid, for some reason I always was fascinated more by the really small stuff, like I was really into, molecules and polymers and all these things, like growing bulk scale things from smaller pieces. I always would joke to my students and anyone that I present my research, when I did research on, I would joke that, I've never gotten over playing with Legos as a kid, and that's always what I loved.
I haven't either. I have the big Saturn V, and I have the ISS, and
I'm so comically jealous of that, and now you need to get off my podcast. That's all. Well, so I guess I sort of wonder, like, the scales you're talking about here, the fact that an explosion like that could still be giving off radiation decades later is so, it's so hard to wrap your mind around.
Yeah, so I actually have what probably like the PhD thesis chapter that I can actually, tell people about most. So I studied a supernova called Supernova 1987A. It's called that because it is the first supernova they found in 1987, and astronomers are very creative at naming things, right?
What a name.
Yeah, and it's also, the interesting thing is, so it's kind of a distance and time thing, that it's actually the closest supernova that we've observed since the invention of the telescope. So
wow.
The telescope, the last supernova we had sort of that we saw in our galaxy was 1604. Galileo saw it, but he didn't have his telescope yet. So since then we haven't really seen one in our own galaxy. And the reason supernova 1987A, it wasn't actually in our galaxy. It was in one of our satellite galaxies called the Magellanic Cloud. So that's about over 100,000 light years away. So the amount of time it takes for light to travel in 1 year took over 100,000 years for this light to reach us. But that's still the best detail you get. And even 30 years later, it's actually brighter now in radio than it was when this explosion first happened, because this explosion keeps going outward. Mm-hmm. And I made little radio pictures and put together a GIF. So I was in charge of like 2013 to 2017. But of course, you have data sets from before, and you can stitch them together and get a little smoke ring GIF of this thing expanding outward still today. And that's really cool also because we don't really know much about how a supernova becomes a supernova remnant, right? So over hundreds of years, thousands of years, it becomes the remnant, can affect a lot of the area around it, maybe make new planets and stars form in that area. But we don't really know much about that transition, and this is a really cool way to be able to study that.
Wow. That's just, so in terms of, I guess, what you do day to day, so that was one question that I know a lot of listeners have when we do these episodes is sort of, what is the day-to-day work of someone doing the kind of research you do like? Are you, I just actually last night rewatched the Simpsons episode where Lisa tries to get all the lights turned off in Springfield so she can see a meteor shower.
My favorite's the comet one, but yeah.
Yeah. Oh yeah. Yeah. So, it's such a funny, it's like, I guess from a perspective of someone just kind of hearing about astronomy and what people do, I think a lot of the time you think you're spending a lot of your time with giant telescopes, right? But what is it day to day, I guess, like doing that kind of work? Or I guess, what is your...
Yeah, sure.
Yeah.
So I think, first of all, it's important to note that you don't really need to go to the telescope anymore, especially in these pandemic times. So I have published papers using telescopes that I've never actually seen. So like the 1987A project is using a radio telescope in Australia, and I've never seen that radio telescope.
Oh, okay.
It's of course it'd be like nice to have the romance, but it's also very expensive to go down to Australia, and like anything though, you have the observer now who takes the data, and then you can download it off the internet, and that's how you get your data.
Sure.
It's also very nice, though, like in this era of social distancing, like I mainly use these days the Very Large Array in New Mexico, which if you've ever seen Contact is like the giant array of dishes that Ellie Arroway uses to talk to the aliens or whatever.
Sure.
For that, yeah, you just put in your request for the observer, and they've been able to keep going in a pandemic, not at full capacity, of course, because there's some social distancing stuff involved. But at least we could still get our data, so that's really nice. And, something cool happens in the radio sky. We've been able to keep working on those sorts of projects. As for the day-to-day, because I'm obviously not going and observing and stuff myself, it really depends on where you are in the project, I guess, is kind of what it comes down to. So first thing in any project is you have to propose for time to do the science you want to do. So usually there's, for the VLA, for example, twice a year, there's a call for proposals. Anybody actually in the entire world can put in a proposal. So if you have a good enough idea, you can also propose. Like high school students have gotten time on the VLA. Granted, it is competitive. Maybe only half the people who apply will get time. So, so you apply for time. Then when you, as I said, you put in your observations, and then finally you can get your data and download it. You have to reduce the data, which depending on the data set can be either straightforward or a bit tricky. And then basically most of the time, though, what you're doing is you're doing your analysis. So kind of explaining what is happening in the data, and then writing up the paper to explain to everybody else what you found in the scientific community. Those are kind of the main things. And then, of course, like you have your smattering of meetings and things like that, like any job has. I mean, I have a virtual summer student this summer. So, working with him and stuff like that on science are also things that happen.
Sure. Yeah. Yeah, I think, it's funny. The one thing that, I feel like we end up telling a lot of our, we have a lot of listeners who have kids who are interested in the sciences and maybe want to get involved, or, even want to know, like, well, what would I do if I wanted to become a scientist or an engineer or whatever? And the one thing I always tell them is get really good at using Microsoft Office, because you're going to mostly be like, you're going to be putting together PowerPoints, you're going to be doing Excel work like 90% of the time.
So actually, or at least for astronomy, we don't use Office as much because we're mainly coding in Python these days.
Oh, okay.
I tell everybody is learn Python. And we also, because I know engineers, you guys will write your papers in Word, but we use LaTeX, which is like this basically computer code to write your papers, which I am not a fan of, but this is not exactly something I'm going to change personally in the field.
I had a master's student who was working on my project send me a paper in that format, and he was like, oh, so just download this thing and then use it. And I was like, man, we're only like 4 years difference in age, and I am too old for this thing you're showing me right now. Like, just
yeah, it looks really, really pretty. It's actually been around for several decades, but it's just some fields it's the default and some it's not.
Right.
We're very particular about where to put everything.
Well, that's good stuff. I mean, it makes sense, right? You're looking for things in the sky and their places, so you got to have it looking nice on the screen. I don't know. So what was it that got you interested in this field as a kid? Or, do you think what led you to take on this career path?
Yeah. So when I was a kid, I basically was interested in a lot of different things, and I would read a lot. And one day when I was 13 years old, I also had an hour-long school bus ride, by the way, home from school. So I would read a lot on the way home. And I was one day, didn't have anything to read, which is, of course, a huge problem. And I had 5 minutes till the school bus went. So I went into the library. For whatever reason, I wanted to read a book on astronomy. So I picked out a book. Still remember it. It was From the Big Bang to Planet X by Terence Dickinson, which is unfortunately no longer in print. But it was just one of these 50 general questions about astronomy type books. And by the time I finished that book, I was basically just this is the coolest thing ever. I want to be an astronomer when I grow up. And honestly, that's never really changed since then. I'd say the only real sort of slight tweak along the way was when I was a teenager and I saw Contact / Red Contact. Then I decided I wanted to be a radio astronomer. basically because Ellie Arroway was super cool and I wanted her job. And that's, I decided when I was 16, I became a ham radio operator and stuff. So, I decided I liked radio and everything like that. And it's a very powerful wavelength, but it's very difficult compared to just, optical. You look in the sky, you see your object. You don't have to do too much else. Optical people get mad if I say that. Compared to radio, you don't have to do too much else. And so that's just honestly been kind of my career path since. I was very lucky that I found my passion fairly early.
Yeah, that's, it's funny. I think that there's a lot of kids like that they figure it out. They kind of figure out or they glom onto something right away. And they're like, this is what I want to do. And then if they had more, like I know when I was growing up, I kind of very quickly figured out that I wanted to do chemistry or some kind of chemical stuff. And then it was kind of hard to find like mentors along the way because, my parents didn't do that sort of thing. None of our family friends did that sort of thing. And I was lucky enough to, in high school, meet a teacher who was a biochemist for a while before she became a public school teacher. So I kind of was lucky to find that mentor. And one aspect, I guess, of what we hope to do on this show, and I think also what you've been doing is science communication, right? So what, I guess, for people that want to get involved in that aspect of this stuff, how did you get involved? What did you start doing to start getting your voice out there?
So first of all, I feel like there's sort of two bigger things I need to split what I do. So the first is the social media side. My primary thing, I think we got in touch on Twitter, but I am actually far more successful in my outreach on Reddit. I don't know if you stalked me over there at all, but so on Reddit, I am Andromeda321. Well, so I start my comments with astronomer here is the given thing. And I actually started doing that. Like I had my Reddit account for, procrastinating like many people do. And I saw something that was wrong on Reddit, like scientifically wrong. So like gamma ray bursts can kill us all or something like that. And I get really annoyed when I see misinformation out there, especially about astronomy. Like it's just a pet peeve type thing.
Sure.
So I actually just wrote a thing where I was like, hey, astronomer here, this is not actually true. We can't actually die because we don't have stars that are within the kill radius for a gamma ray burst close enough to Earth. We can see them because they're really bright stars. And also you need that beam directly pointed at you. And we just don't think that's really a concern. And then that post kind of went viral and everybody was just really I think Reddit gets a lot of bad press, but I've actually honestly mainly had really lovely interactions with people because they were just all like, oh, this is amazing. Thank you so much for telling me. I used to be worried about this and now I'm not. So as getting your voice out there and just telling people things are wrong, somebody's reading. I don't know. I can't guarantee everybody reads. But anyway, so then Reddit I've been doing that for several years now. And I actually have several students who have gone on to become scientists because they thought my posts were so interesting or I gave them career advice and stuff. So that's incredibly rewarding, of course, knowing that you can have that effect on people just from your random Reddit posts.
Yeah, it's amazing.
Yeah, it's been really fun to have that platform. The other angle, I also actually do science writing. So I write for Astronomy Magazine, Discover, Scientific American, the website, stuff like that. That actually I just started. So I was always writing. So before I read the book on astronomy, I wanted to be Lois Lane from Superman.
Nice.
Yes. So I wanted to be a journalist. And then I kind of joke that I'm really lucky that I get to do both, is sort of like kids who want to be like a president astronaut, And so anyway, the writing, I always wrote, I wrote in the high school paper, college paper, I had a column, which was about science topics and stuff like that. And then I actually started during my master's just pitching. Astronomy Magazine was actually sort of the first major publication that I wrote. So it's just, you write a query letter where it's like, hi, I'm so-and-so, I have this idea. You detail it, you have some clippings that you include so they can see that you know how to write. And then that was sort of how the ball got rolling on that. So I'll write a few pieces a year these days for just freelance. So
it's so interesting because that's another aspect of this that I think a lot of people I started this podcast specifically for the same kind of reason, right? I think that you did, which was, or why you started on Reddit, which was people are posting like crazy stuff all the time about all kinds of science stuff, you know, and it's sort of frustrating when you think, or I guess you ask that question of, you know, well, there's actual cool stuff going on in the sciences and there's answers to some of these questions and stuff. But on the other hand, you have people who, it kind of seems like the mystery is the point, you know, you want it to keep going.
It's definitely one of those things. I think most people, it's just the education hasn't been there versus like a willful ignorance or something. Like, I don't quite know how to phrase it. But I think most people, like if you explain it, people really do want to know what exactly is out there and what the truth is. And I've always thought, like, one of the reasons I really like astronomy is it's the biggest story we have, right? Is the story of the universe, how it came to be, and what's going on in it. I think that's very powerful. My dad likes to say when I was a little kid, I was always obsessed with asking, like, did that really happen? So, like, I really liked fairy tales and stuff. But then, you know, it kind of get this point when you get older that you learn that they're not true. For me, science is amazing because it's like we know all these fantastical things are true, you know, of course, to the best of our scientific ability and everything like that. But it's really very powerful for that in terms of the excitement I get out of it. I feel it's like what I used to feel for fairy tales when I was a kid. So that's kind of what I like to convey about it is there's a lot of really cool, exciting things, and we know that they're really real. So,
yeah, no, 100%. Oh my goodness. It's so, I can't wait to now go on Reddit and read all your posts because I didn't know that was you. I can't believe I didn't know that before you got on the episode.
Did you know? Oh my gosh. Did you, do you know the account then?
I remember the post actually. Yeah. I don't remember, like, it's crazy
There's been a few AMAs and stuff.
Oh my God.
There's a subreddit, like, so reddit.com/r/Andromeda321.
That's so cool. Oh my God. Yeah, no, totally gonna go check it out now. That's so awesome. It's funny. I've had the opposite experience, at least, where kind of the podcast and like Twitter and Facebook have been really good for science outreach through this. And I think it's mostly because, you know, frankly, I think it's partly because of the topics we cover and the way we come at them. And, you know, we throw a little bit more of like the spooky stuff out there. And Reddit, we've had some success on generally, but it's never caught fire. Right. So it's cool. It's cool though to hear that, you know, I don't know, we should keep trying.
Yeah.
We'll give it a go. We'll see.
Make a subreddit, see what happens.
I'm telling you, right? That's what we'll have to do here.
So I did actually give a talk once at the International Astronomical Society. They do a Communicating Astronomy with the Public conference every 2 years. Well, not this year, but, you know, normally every 2 years. And I talked about Reddit. And the thing about Reddit that's really important, a lot of people forget, is it actually has such a huge number of people. Like, it has more people than Twitter on it, for example. So it's not just like another social media thing you have to do. It's actually like important in terms of like, there's a lot of people you reach if you're on there, if that makes sense.
No, it totally does. Yeah. I mean, it's the law of big numbers, right? All right. So we talked about some of the science stuff. Now we're going to talk about the weird stuff.
Yes.
Favorite science fiction movie of all time?
Ooh, well, it has to be Contact.
Contact. Oh, it's so cool. Okay.
Yeah. So Contact is, as I said, I saw it when I was a teenager. So it's very near and dear to my formative years. So it's like, you know how people these days, when they ask like, what's your favorite book or something like that?
Sure.
You know, I have some favorite books, but nothing really grips me as much as stuff when I read, you know, when I was younger.
Absolutely.
Yeah. So it's kind of like that for me in Contact. It's like, more recently, like, you know, Interstellar was fun, but man, Contact, that was a great movie.
Yeah.
So the movie Contact, it was the book was the first thing written by Carl Sagan. Also, like, I basically just wanted to be Carl Sagan when I grew up. That's probably the other reason I was interested in outreach.
Sure.
But then he wrote it, and part of the reason his Ellie Airway character exists is she was inspired by his friend Jill Tarter, who's head of the SETI Institute. And Jill Tarter, basically, I worked for her one summer when I was an undergrad as like a summer intern. And so that was really cool. She has a picture of her and Jodie Foster on her wall in her office, actually. And yeah, she's just a very, very cool woman. So it was cool to say, you know, I finally met sort of the person who in many ways inspired me to do it. Because, of course, it was a fictionalized version of her. But, you know, she's a real head of the SETI Institute. And she also, unfortunately, lost her father at a young age. So there are a lot of, like, storyline arcs that are similar in both people. So...
Cool. So contact. So I mean, I guess the inevitable question here: aliens. What do you think?
I think they're out there. I don't think they come here to draw crop circles and fields and never tell anyone about it.
Sure. Yeah, they're probably not communicating via corn.
Yeah, the one that kind of entertains me is, so at some point, I was learning like the introduction to my PhD thesis or something. And when I was doing this, like I was looking at sort of the original real radio inventor of radio astronomy. His name is Carl Jansky. And he was doing this in the 30s, some radio experiments, and he basically detected the center of the Milky Way in radio, which is, one of the brightest radio sources in the sky. And there's a New York Times front page article about this, which I found. And it says at the end of the article, Jansky says basically that this is not, a signal. It's very unlikely that it's from an alien civilization. So basically, radio astronomers have been telling people it's not aliens since the beginning of radio astronomy. So I always thought that was pretty good.
I was gonna say, I think it's funny, we've interviewed a number of archaeologists as well on the show, and I think you guys could have a really good argument here about who has been for the longest time telling people that wasn't aliens between archaeology and astronomy.
I mean, their field is older than mine, so probably literally them, just
right,
for that reason. But yes.
Yeah. Oh, that's so interesting. So one part of that question, though, I guess, or one thing that I always wonder to myself, because one of the, for me at least, one of the most important things you can learn in the sciences is that you don't know everything, right? You know a very small part of one thing. And one thing I've always wondered whenever I see those articles like that, about a signal coming from deep space or anything else, how noisy is space? Like, how much signal, yeah, you know what I'm saying? Like, how hard is it to separate signal from noise?
Yeah, I'm trying to think of just how to explain it for a second here. So the trick is actually that it's not necessarily that space is really noisy or not. It's more that radio signals are very weak. So if you put a cell phone on the moon, for example, that would be one of the brightest radio sources in the sky. Is really kind of like, just think of something that by Earth standards, that's not a lot of power being output, but it's actually pretty crazy in terms of like radio astronomy signals. This has to do also back to that electromagnetic spectrum. Basically, radio waves are very low energy compared to higher waves. So like X-rays and gamma rays are very high energy. That's why, you can like fry stuff with a microwave, right? And so that's like a very high energy wavelength. We're so low energy that if you have a snowflake that melts into a drop of water, that process has more energy than all the radio waves we have ever collected in the history of radio astronomy. So this is pretty faint stuff. So compared to that, like astrophysical processes are by and far very, very bright compared to anything that we can really generate on Earth. This would actually be one of the things, if you want to like talk, use SETI as communication, it's actually getting to the energies required to like have a very bright signal is actually very difficult. Where technologically, it's not like they're really going to pick us up very easily, even at Alpha Centauri. So in that context, like most of like, if you were to just, point your radio telescope to a patch of sky, like most of it's not particularly noisy or anything like that. It's basically the question is more like you're going to have a background level of noise depending on usually like the sensitivity of your telescope. So like the unit, because Carl Jansky, was the pioneer of radio astronomy, our unit is called the Jansky, which is basically like, so in engineering, you use decibels, right?
Sure.
So this is like times 10 to the minus 26.
Got it, okay.
It's like absurdly down there just because we can't really use the same scale. Like it just doesn't make sense. So like, in terms of signals in the sky, the sun is a few thousand Janskys. A bright radio source is maybe a few hundred. One Jansky, I'd already be like, oh, that's fairly bright. Most of the stuff I deal with is in millijanskys. And then the threshold for the VLA will be like, 0.1 millijanskys or something like that.
Okay,
it's a really good observation.
Got it.
Yeah. So that's really kind of it. Like, it's not as much that everything is really noisy as much as it's just the signal processing is very difficult and there's just not much energy in it. So
I mean, really, it sounds like if there was, from the perspective of, I guess, kind of, thinking about these questions in a we like to say that here on this show, we try hard to look at the kind of, the paranormal claims, the weird claims, UFO claims, whatever, in a serious way. So take them seriously at their face and then see if they make sense physically, right? So if we were to think there are UFOs floating around all over the place, abducting our cows and pushing our corn and wheat down and whatever, essentially they would either have to be impervious to radio signals or not outputting any radio signal, I guess. Not really impervious, but not outputting any signal, because we would notice that because it would be so bright.
I mean, so there is a slight caveat. So because I just described all these situations in which, by far the biggest thing we detect at radio telescopes is man-made interference. We call it radio frequency interference, RFI. A lot of it you actually just automatically filter out because you cannot deal with looking at all of this. They used to do hand flagging is what it was called back in the day, but these days you usually run your data through a pipeline. So if it's like a very narrow band signal, I just filter that out because like radio astronomy, what I mean to say narrow band, I mean one specific frequency. So you tune your radio station to 89.5, right? Megahertz.
Right, yeah.
So those sorts of signals, like astronomical objects don't really do that. So I'm just like, I don't really care as much about that. So I just filter it out. That said, though, if it's like, they're on their way into the solar system or something like that, I would probably notice because, you'd also be like checking with multiple telescopes and stuff. So some observations you're using VLBI. And so if something is localized, then you can tell versus if it's like, some telescope far away sees it. So you would notice like that. I think, so if you had aliens, coming to talk to you, so one of the famous ones in radio astronomy is called the WOW signal.
Yep.
And so, to be fair, like in my own research, I always say that the aliens come to call, then I would pick it up, but I'm not like actively searching for them like 7 people are.
Sure.
And so something like that where you had like a random signal that was from, I've heard before that a satellite, if like it was in a polar orbit and this and that, could have caused that same signal. And these days we do recognize, or I heard this, so I don't know if it's like 100% true from somebody who was working at SETI Institute, that these days you would filter that out because we know that a signal that causes that is just man-made interference because they've done some tests. I don't know if that's 100% true, but honestly, you see so much man-made interference. It's like hard to describe. It's like a million times more than, the astronomical ones.
Sure. No. Yeah. Well, I was, it's interesting that you like that filtering of the noise again. It's such a, what kind of computers do you need to use, or what sort of, are you working with? I mean, the signal itself, I guess, removing of that signal wouldn't necessarily be that computationally heavy or difficult necessarily. But I'm wondering, like...
It depends on the project. So sort of the computationally, the most intensive one I worked on basically had, a super correlator because they were processing like a DVD of data every second. It's kind of the equivalent. So that's like the very extreme end. And you have supercomputers and this and that processing this. That's like, it depends on if you want to do it real time or not. I'm not as interested in the real time. I'm usually logging into, there's the National Radio Astronomy Observatory has supercomputers, and you can log into the machine and use them as part of just using their observations and stuff like that. So that's usually what I'm doing. I'm usually like if it's a small enough, like it's a few gigabytes per observation. Of course, it depends on the length of the observation. Mine are usually a few gigabytes. So I'll do like some stuff on my own laptop. I just have a laptop. I don't have like anything like a big PC or anything on my own machine. It's just my MacBook Air.
Sure.
So I usually just log in these days and use another supercomputer. I'm not going to be doing it on my own desk. So.
Got it. Man. Yeah, it's interesting when you think about so one question we always ask, and we got a couple minutes here left, so I want to ask you the 2 questions we tend to always ask in these interviews. The first one I'd ask is what do you think is the biggest improvement in your field, or what do you think is the most important thing that's happened for your field in the last 5 years, and what do you think the next big thing might be?
That's an interesting one. So biggest improvement. I think one of the biggest improvements, so like in radio transients in general, there's been this thing called fast radio bursts. And so these are basically these one-off bursts where these signals are basically millisecond long pulses that appeared to come from beyond the galaxy. And I just described how hard it is to get to those energies, right? Basically, if something is one of the brightest radio things in the sky and coming from very far away, it's impossibly difficult. I think theorists still haven't figured out how these things should exist. The trick is now, though, if you know, like, of a few thousand of them, then okay, it's probably a real thing versus just some artifact in your data or something localized to Earth or something like that. They also appear to come from all over the sky, so probably not aliens because, you know, if they're spread over everywhere astronomically billions of light years away, it's hard to believe the aliens would be everywhere but not here, right?
Right.
Anyway, so yeah, there were like a ton of questions about what exactly these things could be, and it was very unclear. I think, though, the field has really changed in radio transients that now it does appear that there's are something called magnetars involved. I think most people would agree, at least for some of these, that this is what's causing it. So a magnetar is after a star goes supernova, then you have basically a neutron star can be left behind. It either collapses into a neutron star, collapses further into a black hole. It depends on the size of the star that's doing the exploding. And some neutron stars basically have neutron star is basically a ball of neutrons that's maybe the size of a city, so like 10 kilometers or 10 miles across or so. Mm-hmm. And some of them have very, very extreme magnetic fields. So that's what's called a magnetar. A magnetar, basically, if you got within 1,000 kilometers of one, you would die because the electrons would be stripped from the atoms in your body. Like, that's how extreme these magnetic fields are. And now it seems, because there was something that's very similar to a fast radio burst, actually a few months ago, that was observed that was, you know, not quite at that energy level of these ones that come from well beyond the galaxy, but pretty close. And there's been stuff like that. So it does appear that these bursts these fast radio bursts do appear to be related to the magnetars. So I think that's really cool that there's been this mystery during the course of my PhD, basically, where we didn't really know what it was, and we only had like a very small individual number of these bursts, and now it's become its own little subfield with conferences and things like that. So that's been pretty cool.
Yeah.
What was your second question?
No, it's okay. It's okay. The second question, I guess, was, what do you think? What's the next mystery to be solved? What do you think the next kind of development that might happen that would be really exciting would be?
Can I give you two?
Absolutely.
Okay, so the first one that I'm really hoping for is a galactic supernova. And so what I mean by that is, as I said, the closest one that's really happened in recent observational history is supernova 1987A, but that was still like a satellite galaxy, not our own Milky Way. And there's so many questions about a supernova that if we had a supernova in our own galaxy, it would just probably immediately answer a lot of these questions. Because most supernova are so far away, it's just a little point source. You can't really see any detail on it. And if you had one, like, it could potentially be so bright that you'd see it in the sky for 2 years and be able to read by it and stuff like that, right? So, that would really... The big problem, actually, at that point is you can't point a lot of the major astronomical telescopes at these objects because it would just be too bright if you had a galactic supernova. But yeah, we haven't seen one. As I said, the last observed one was 604. It doesn't mean that we don't think they've happened, to be clear, because as I said, there should be one a century or so. It's just There's a lot of dust, and it was probably behind dust, and we didn't have radio telescopes until Karl Jansky.
Got it.
These days, we would be prepared, even if it was behind a dust cloud, and we would learn a ton of information, and that would be really cool. The second one that... to go back to the tidal disruption events. So the first tidal disruption event, so this is pretty recent. It was discovered in 2011, and it's called Swift J1644 plus 57 because astronomers are amazing at naming things. Swift was the telescope that discovered it, and then the numbers are the coordinates, basically, for this object. And it basically launched a relativistic jet. It was like 2 billion light years away, but it launched a relativistic jet pointed directly at Earth. Basically, when the star got too close, half of the material of the star fell into the black hole, half formed this jet and this shockwave and everything like that. And then after about 2 years, this jet turned off. So it was like a very unusual system. Since then, we've seen maybe about 100 tidal disruption events at various frequencies and stuff like that. Never seen another one of these jets. So we like relativistic jets. We're pretty confident you can also tell that it's not that, the jet just wasn't pointing at us or something like that. Like, it just looks like this legit hasn't happened or doesn't happen very often. And basically, we have no clue what's going on with these relativistic jets and how these black holes are tearing apart the stars. There's still so many questions unanswered. So I'm basically like, you know what? We could really use another one of those. It's been like 10 years. Like, let's get another one, and then hopefully we could answer some of those questions.
All right, so we'll all keep our fingers crossed.
Yeah, if you can order one for me off of Amazon, that would be really
right. Yeah, we'll we'll all hope. I'm gonna have to add relativistic jet to my Google Scholar announcements or ping, so I'll know when to email you and be like, hey, it happened.
Yeah, it's also just really weird because everybody's like, oh, but like, how does the relativistic jet happen? And I'm like, we don't know. That's the point. Like, there's a lot we don't know in astronomy, and it's just like, yeah, it would be really cool. At least if you saw a few of them, you'd have a chance of figuring it out. But if you only have one event that's really, detailed, it's a lot harder.
Yeah, absolutely. Oh my goodness. All right, cool. Well, I feel like I have learned so much already just from the small time we've had talking to you. I'd love to have you on again sometime in the future. I mean, maybe we'll be celebrating one of these relativistic jets. Fingers crossed. But
yeah, sure. Well, let me know if something cool happens. I'm probably up for talking about it because I don't know if you can tell, but I can talk a lot about things I'm passionate about.
It's great. It's you know what? If there's one thing I really wish that we taught students in the scientific fields, it's how better to communicate their science to the public. Because otherwise you get cases where, stuff. I mean, I don't know if you've never met a scientist in your life, if you've never really engaged with the sciences, then first off, how do you know how to become a scientist if you're a kid interested in this stuff? But also, why would you trust someone, a type of, profession you've never met or interacted with, right?
Oh yeah, for sure.
So, and as part of that, actually, the last question we have is, if you had to suggest, like, we have a parent listening whose kid is super into, I don't know, explosions or space or any of this stuff. What is a good book you'd say for them to read? Is it Contact? Is it, is it that other book that you mentioned before? Like, well, that one's out of print, but what would you say is a good way or a good place for them to start learning about this stuff as a kid or even as a high school student?
Yeah, so I actually feel like I have a tough time recommending books because I don't keep usually up at the latest stuff, because usually if I'm like, sitting at home or sitting at work doing astronomy all day, I actually have a lot of other interests. So I tend to like study those.
Sure.
I do know, I have a friend, Katie Mack, is coming out with a book called The End of Everything, Astrophysically Speaking, next month. And I'm really excited for that one. I'm going to be checking that book out. Sort of because I know some people also just like the history of science. If people are interested in like where I work and stuff, there's actually a really cool book called The Glass Universe by Deva Sobel. So these are unfortunately more like teenagers or adults for like this level of book. But yeah, so Deva Sobel wrote this book called The Glass Universe, and it's basically a century ago, or a little over a century ago at Harvard, basically studying the universe. You would take exposures on glass plates, and you would develop those, and that was like the beginning of astrophotography. And basically these women were hired because it was unseemly for them to use the telescope to basically process all this data, and they were called computers. And then these women ended up discovering and basically creating modern astrophysics. They're the ones who figured out the types of stars. The size of the universe was basically figured out based off of their observations and all these different things. And that's kind of, she goes into the story of how, like, these women and like how my institute became the institute I'm at today. So it's a very cool read. And if people are interested in sort of the broader stories of how people do science, I'd recommend that one.
Absolutely. Oh my goodness. It sounds like I'm going to have to pick up that book. That sounds great. Oh my goodness. Well, thank you so much. So Dr. Yvette Cendes, thank you for coming on the show, talking to us today. Listeners, please go check out Dr. Cendes' work. Go to reddit.com/r/Andromeda321. for all of the baby loon action that's going on right now. And yeah, you know, follow her on Twitter. And yeah, thank you so much for coming on. We would, like I said, love to have you on again, and we'll talk soon.
Yeah, sure thing. Have a good one.
Thank you again, dear listeners, for listening to the Mad Scientist podcast. I have been your host, Chris Cogswell, joined by my co-host,
Marie Mayhew.
If you'd like to contact the show, please send us an email at themadscientistpodcast@gmail.com. That's all one word. You can also follow us on Twitter at Mad Scientist Pod or at Team Giant Squid for Marie. And of course, you can see us on Facebook, on Instagram, and all over the internet as the Mad Scientist Podcast. And again, our logo is the one with the pumpkin head, so it's easy to see.
Mm-hmm.
If you've enjoyed the show tonight, please consider supporting us on Patreon, where the money that you give to us will help us to promote this show further, to make it better, and just to spend more time making it.
Because we love doing that.
We do love doing that. Our logo was designed by Carrie Shaheen. Our web design is done by Desdemona Howard.
Woohoo!
And our sound design is done by Jake Carter.